From University of Norwich.
Thanks, Jim. And thanks to Takis and Kavita for inviting me. So I'm going to be talking about scheduling in wireless networks with flow level dynamics. I added the with flow level dynamics after I originally gave my title and abstract. I was going to give a slightly more general talk, but then I've been working on this the last month or so I decided to focus more on this.
I can't hear you very well.
I don't know. Is the mic working?
So not one, let's just maybe switch it.
Seems to be on. Hello? Maybe it's should we put it somewhere else? Can you hear me now? How about now? No?
Can you adjust the volume? The volume setting.
Where is the volume switch?
It's on. It's fine. It's working fine.
They can't hear me. Okay? Okay. Okay, I'll be louder. So I'm going to be talking about wireless networks. So in general, a wireless network consists of a bunch of infrastructure nodes that are sort of in place, like a tower that's transmitting energy, okay? And mobile nodes, which are possibly moving around. They come into the network and they leave the network, and then they talk to each other through these mobile nodes, or possibly directly to each other. Okay? So there are dynamics in these networks at multiple layers. By layer here, I mean layer in a communication network. So you have channel dynamics. So when for example, this tower is talking to this mobile, this channel might be time varying. So the rate at which you can transmit data over this channel can vary from time slot to time slot. Okay? And of course, we have packet dynamics. You have bursty traffic flows. And these are two things that have been studied very heavily in the wireless network scheduling literature. So people have developed throughput optimal algorithms that take into account channel dynamics and packet dynamics. Something that's not been studied quite as extensively is flow dynamics. So by flow dynamics, what I mean is that these users arrive into the network, transfer a certain amount of data, and then leave the network. Okay? In general, most of the literature assumes that you have a fixed number of mobiles in the network. Okay? And of course, there's also interference. That's something that I'm not going to consider. So in general wireless networks, when two people are transmitting at the same time, their signals interfere with each other, and that limits your ability to communicate. But that's something that I'm not going to talk about today. Okay? So the problem that I'm going to look at today is scheduling in multi-channel wireless networks. What I mean is you have a base station here. Okay, base station is this fixed infrastructure tower kind of thing that's transmitting to these mobiles. And this base station can communicate to the mobiles in one of multiple channels. So you can think of the system as having multiple servers and a collection of queues, and each server can, or each channel or server can access one of these queues at each time instant. So each channel can access only one queue at each time instant. So this red channel and the green channel can each serve one user in each time instant. Of course, they can serve the same user also at the same time instant, but each server can only serve one user. And the channel conditions, as I mentioned earlier, fluctuate over time. So meaning that if you schedule a particular user, this user, let's say, over this channel, there's a certain rate at which data can be transmitted, meaning a certain number of packets can be transmitted over the channel. So let's call that RIFT, which is the number of packets that user F can transmit over channel I at time instant T. Okay? This information is assumed to be known to the base station, which is the one that makes the scheduling decisions. So at each time instant, there is some information collected about the channel, so that a base station knows if I schedule this user for transmission over this channel, then I can get X packets through. Whereas if I schedule some other user on this channel, then a different number of packets can be transmitted, and so on.
But Srikant, when you say serve, you don't mean instantaneously. You mean within some.
No, instantaneously within the time slot. So the channel conditions are time varying.
Within the time slot.
Exactly. Yeah, within the time slot, so that if depending on the conditions around this mobile. Okay, so this channel could vary. So if this mobile is moving, for example, then sometimes you might be able to transmit 2 times. Typically, a scheduling time instant is like 10 milliseconds in a wireless network. So within 10 milliseconds, you might be able to schedule 2 packets or 3 packets or 5 packets or 1 packet or no packets at all.
Separate question. Are you using index F because flow is equivalent to
User, yeah.
user?
Yeah, flows and users are the same things. Exactly.
And
Yeah. So when sometimes we might talk of a channel state is a vector of rates that can be supported by a channel at a time instant. Okay, so that's what we mean by channel state in this talk. So the traditional model, first I'm going to talk about the traditional model. In the traditional model that people have looked at since the early 90s, you have a fixed number of flows or users, so the number of users is fixed, and packets arrive to each that need to be transmitted to each of the receivers. Okay, the channels are assumed to have some the channel states have some steady state distribution. So based on that, you can calculate. Oops. So if the arrival rate to this user is lambda 1, this is lambda 2, this is lambda 3, whether the system can support the set of arrival rates. So this can be, of course, knowing the channel state distributions here, you can compute what the capacity region of this network is, right? So based on that, you can figure out whether a set of arrival rates or the injection rates of packets into these queues can be supported by the network, in the sense that is there a scheduling algorithm that stabilizes all the queues in the network. Okay? And the goal often is to find a scheduling algorithm that that stabilizes every vector that lies within the capacity region without really knowing this vector lambda, nor knowing the arrival statistics or the channel statistics. So that's been the sort of the a focus of much of the research in this area. So the classic algorithm for this model is the max-weight algorithm due to Tasioulis and Ephremides, which suggests the following. What it says is that on each channel, what you do is that look at the queue length of a flow, multiply that by the rate at which you can serve that flow, and whichever flow has this largest has the maximum value of this q times r quantity, you schedule that flow. So if you have multiple flows that have the same quantity, then you break ties at random, for example. Okay, and this has been generalized in a bunch of directions for wireless channels by many people, and in even other contexts by Jim and Wook-Win Lin. And this algorithm is known to be throughput optimal, meaning that as long as the arrival rate lies within the capacity region, the queues can be stabilized. Okay, and this model handles both channel dynamics and packet dynamics. So the one thing it does not handle is flow dynamics, meaning arrivals of flows or users, and departures of users. So I want to motivate this talk by this simple example, this really neat example that Van de Ven, Borst, and Sneer came up with last year, where they show that max weight scheduling may not be throughput optimal when you have flow arrivals and departures. So let's take a very simple example. You have only one channel in this network, meaning there's only one server, and the channel can serve either 2 packets with probability half or 3 packets with probability half. Okay, so in each time instant, the channel can schedule either 2 packets or 3 packets. Okay, so let's say all files have file size 3, meaning that a user arrives, brings 3 packets into the network, and if the 3 packets have been transferred, then the user departs from the system. Okay, and if the file size is 3, let's say the user arrives, and if the channel state is also 3, then the file can be served and the user departs. On the other hand, if the file size is 3, the file size is always going to be 3. If the channel state is 2, then you serve 2 packets, and then 1 packet remains in the system. Okay? Again, a new file arrives, and the same thing happens. So whenever a new file arrives, notice that under the max weight algorithm, the new file always gets priority. Independent of what happens, the new file always gets priority. Whether the channel state for the new file is 2 or 3, this gets priority because it's going to be 3 times 2 or 3 times 3. So it always gets priority. And it's going to be served, in this case, if the channel state is 2, it's going to be served at, so 2 of the packets are going to depart and 1 packet is going to stay in the system. So what is the maximum arrival rate this policy can handle? So with probability half, it takes 2 time slots to serve your packet, because there are 3 packets in the system. Okay, when you arrive, if you can only serve 2 packets, later on you're going to have 1 packet which has to be served at some point, so it's going to take 2 time slots to serve a file. Okay, yeah.
Can you serve 1 packet from each of 2 files?
No, you can only schedule 1 user at a time. So that's the assumption. Yeah, and that's a technological limitation. Yeah. So on the other hand, sometimes with probability half, it takes just one packet, one time slot to serve because you have three, you can serve 3 packets with probability half. So the maximum arrival rate that can be supported in the system is lambda less than 2 over 3. Okay, is this clear? Okay. On the other hand, let's say we use a different algorithm. We say that we'll serve a flow only if its channel rate is 3. If you can serve 3 packets at a, you serve the flow, okay? Otherwise, you don't serve the flow. Then what happens is that when so let's say the arrival rate is lambda. If there are lots of users in the system and the number of users in the system becomes large, then there's going to be somebody in the system who can be served at rate 3, right? So the probability that you cannot serve anybody under this algorithm, so the probability you can serve somebody under this algorithm goes to 1, okay? So the maximum arrival rate, file arrival rate you can handle in the system is 1, which is clearly much significantly bigger than 2 over 3, right? So sorry? Okay. Repeat, please. I'm lost.
About this algorithm, yeah.
This particular algorithm?
Yes.
Okay, so you schedule, so the channel states of each of the users is independent. Okay? So when there are many users in the system, there's going to be somebody you're going to be able to serve at each time instant. So the number of users in the network will be bounded as long as lambda is less than 1. So you're going to be always able to serve somebody in the system. Okay?
So this is like analogy in the manufacturing settings. If you want to start an oven to bake something, load the job, load the oven full, start the oven, right? Don't
Okay.
start the oven half loaded.
Okay. What are you cooking? Cakes or?
They make silicon wafer, silicon
Okay.
wafer.
Okay.
Yeah.
I know.
Yeah.
I'm just kidding. Okay. So probably is a diet control mechanism too somewhere there. So what this simple, really neat example I think illustrates is that max-weight algorithm. The max-weight algorithm may not be throughput optimal when you have flow-level dynamics. Okay. So the reason that the max-weight algorithm works in the traditional model is that when the set of flows is fixed, when a queue length builds up, okay, so you know that it's not receiving enough service, and so you have to start giving higher priority to it. Okay. Whereas here, a flow is interested in uploading and downloading a file of a fixed size, so backlog doesn't build up ever. Okay. So backlog is not a good indicator of anything in this network. Okay. So we need something else to schedule flows when there are flow level dynamics. And this is something that's been bothering me for a long time. I've been talking to people at Motorola and Qualcomm for the last 10 years. They all say they use some version of the queue length based algorithm for scheduling. If you look at many 3G and 4G networks, they all use some version of the queue length based scheduling algorithm, but they all say they have to do some fix. I mean, they hack it in some manner because it doesn't work sometimes. Okay, and some people I know, a guy named Tom Richardson, who's a senior vice president at Qualcomm. They are building one of the world's first ad hoc wireless networks, not a base station type network, but where people are just sitting in this room and they all have a laptop and they're trying to talk to each other and so on. And I've been suggesting to them, why not use queue length based scheduling algorithms? And Tom told me that it doesn't work for them because all their flows, they expect all the flows to consist of just like 2 or 3 packets. And he says that I don't want to use these algorithms because they assume that you have persistent flows. And so the question is, so I think there has been so they've been doing simulations and they noticed that this has not been working very well sometimes. So this is I think this example by Van de Ven, Borst and Schneer I think sort of partially points out to the issue in such networks. Okay. So what they further do in the paper is that they suggest some other type of algorithms, but the algorithms require full knowledge of the network, meaning that they assume channel statistics are known, arrival statistics are known, and then they come up with throughput optimal scheduling algorithms. And they leave this problem of, are there online algorithms with good performance? So are there algorithms which don't need to know the channel statistics, okay? And do these perform well? And the answer to that question is yes, and that's what I'm going to be talking about. Okay, is the motivation clear? Okay. So the model here is that you have, so first I'm going to take a somewhat trivial example. It's just a single channel. In this case, the answer is relatively easy, but to motivate the multi-channel case, I'm going to consider the single channel case first. So you have a network where there's a base station, as I said before, and transmitting to multiple mobiles. And I'm going to right now assume that there's only one shared channel with a finite number of states. And the channel states are independent across flows. And mobiles arrive and depart. So a new guy joins, and then some guy who has finished downloading his data or departs from the system. And the one assumption I'm going to make is that file sizes are upper bounded. This is not critical for the talk, but I'm going to assume that right now file sizes are upper bounded. Okay. So in this case, of course, since the number of packets in a file is bounded, okay, the notion of stability is different. So you're not looking at queues building up, but you're looking at the number of users in the network going to infinity. So you want to bound the number of users in the network. And what is so let's just first try to understand for this very simple model, what is the necessary condition for stability. So let's say a flow has file size f, okay, and let's say R max is the maximum data rate available to that flow. So as I told you, the channel rate fluctuates up and down, okay. But there is some maximum rate at which you can transmit. If the channel conditions are really, really good, nobody turned on their microwave near you. So in that case, your channel condition is really good. There's no interference, and so maybe you can transmit at a certain rate. But given the technology, there's always a maximum limit at which you can transmit, so let's say R max is the maximum rate at which you can transmit. And the minimum number of time slots that you would need to transmit that particular flow would be f divided by R max, right? So f is the number of packets you have in your flow, and R max is the maximum rate at which you can transmit. So you need at least this much time to transmit this file. Okay. So which means the amount of work you're bringing into this network. This is lambda is the number of files per second arriving into this network, and this is the number of files per time slot. This is the number of time slots it takes per file per file to get transmitted, because this is the expectation over files, and therefore this has to be less than 1. So this is the necessary condition for stability in a single channel network. It's very simple, right? So what should you do in this case? Suppose, let's just say for right now, you know the maximum rate at which a file can transfer data. So file arrives, somebody magically tells that file this is the maximum rate at which you can transfer. So there are many files, and depending on the channel conditions, the maximum rate could be different. But let's say that somebody tells you what's the maximum rate at which you can transmit. Then what you should do is that you should transmit a flow which is in its best channel condition. Okay, so look at each flow and look to see whether its channel condition is the best that it can see, and then transmit if the best channel condition it can see. And clearly this should work, because when the number of flows is large, with high probability some flow must be in its best channel state. Okay, so therefore you're reducing the workload by 1. Okay, so another way to state it is that this is the arrival rate of workload. So this is lambda times, so there should be an expected value here. F over R max is the rate at which workload is arriving. And let's say that there's a lower bound on the probability that a particular user can see its best channel state. So the probability that no user will see its best channel state is 1 minus p max times n power t. So when the number of users is large, clearly if lambda times this quantity is less than 1, you have stability. So the total workload in the system will be bounded, right? So clearly there are issues with this simple algorithm, because how do you obtain the maximum rate? So how do you obtain this RF max? So you don't know this RF max, so how do you know this? Okay. Also, how good is the performance of this algorithm compared to the max weight algorithm, for example? Okay. And we will address these issues later. But the main point of the talk is I want to see how this algorithm gets more complicated when you have multiple channels. Okay. So if you look at current and next generation wireless networks, you have multiple channels available. So this is based on something called OFDM technology, and you have multiple channels available for each user to transmit over. Okay, and a user can transmit on any one of these channels. Okay, of course, as I mentioned before, only one user can be transmitted on a particular channel, but a user can access any of these channels. And so this is a notation that I introduced. So the state of channel I to flow F is given by Ri of t.
network decided that or user decided?
Sorry, yeah, the network decides that. So in this example, in this model, the base station is the one that controls everything. So the base station actually gets feedback about the state of all the channels in the network, okay, and based on, and it knows the queue lengths of all the users, and then it decides how to, how to transmit. So if the question of how to do this in a distributed fashion, if there is no centralized controller, it's a much harder problem.
And your RIF, they're still independent across flows of it.
Right. So I'm assuming that these are independent across flows. Yeah. So that's a critical assumption. So we're assuming that the channel states are independent across flows, which is a reasonable assumption if the channels, if the mobiles are sufficiently far apart. As the number of users goes to infinity, I mean, if it becomes very, very large and the mobiles are all starting to crowd next to each other, of course, this assumption will start to break down. But in real networks, of course, you cannot let it go to infinity. There's actually a finite maximum limit in which at which the number of users is upper bounded. So I guess even though in theory all of these results study stability of the number of users, in our simulations we also look to see what happens to blocking probability, which is probably actually a better measure of performance in a real network, because in a real network the number of users is limited, and once you hit that threshold then you cannot add any more users. It turns out that the algorithms that I'm going to propose actually also work well in terms of blocking probability, much better than max weight algorithm or anything else. But we can't prove that that's the best algorithm in that case. I think that's an interesting open problem. But right now I am assuming the answer to your question is yes. I'm assuming that these are independent across users. Okay. So in the case of multi-channel networks, now how do you even define workload? Okay, so what is workload? Because you have multiple channels. So in the case of single channel networks, you look at the file size and divide it by the maximum rate at which you can transfer, and that is the workload, right? So the necessary condition for stability is simple. In a multi-channel network, it's not at all clear. And this is a very trivial example, but again, just to illustrate a point, I'm going to just go through the example. So for example, would it be sufficient for each channel to select a user which is in its best channel condition? So before, for a single channel network, the throughput optimal solution was just to select the user which is in its best channel condition. But in a multi-channel network, would this be throughput optimal? And the answer is no. So if you have a network with two channels, both transmitting at constant rate 2 and 3, okay? So in this case, it's just the channel rate is constant. It doesn't even fluctuate with time. So this maximum channel rate is fixed, okay? So you can schedule any user over any channel according to this max rate rule. And suppose you have two types of users, one with file size 4 and one with file size 5, and there are two types of channels, one which transmits 2 packets per second, another one transmits 3 packets per second. And let's say you allocate this user to this channel and this user to this channel, then the maximum rate at which these arrivals can occur is lambda equals 1/2. So the number of flows that can arrive is half a flow per time slot. Okay. On the other hand, of course, if you schedule this file on this channel and then this file on this channel, then the arrival rate that can be supported is half for this file and 1/3 for this file, right? Okay. So clearly, depending on how you assign, it's not so just assigning based on the best channel condition for each user is not a very good idea. Okay. So the question is, what do you do? Okay. So what I'm going to do is, when a user arrives, okay, we are going to decide how many channel users are we going to allow that user on each channel. Okay. So I'm going to say HIF is the number of channel users that flow F is allowed, okay, on channel I. Okay. And so what the H is a vector. So this H is a vector. So suppose I say that this user is going to be scheduled on this channel. That means it's going to be given 2 users on this channel and no users on this channel. Or it could be, so in this for this user, for example, it's 0, 2. Okay. Similarly, if you schedule the other way, it's 0, 2, and 3, 0. In general, it could be more general. I mean, you could allocate this user to use this channel for 2 time slots and then this channel for 1 time slot, for example. Okay. Then you have a different vector. Okay. So what you're going to do is that when a user arrives, you're going to decide how many channel users you're going to give to that user on each channel. So therefore, if you think of it this way, there is a way to write down the necessary condition for stability. So let's say lambda kf is the arrival of class k. So I forgot to mention what class k is. A k a flow belongs to a certain class if the vector of maximum rates that sees on so two flows belong to the same class if the vector of maximum rates that they see on all the channels is identical. Okay, let's just define that to be a class. So let's say lambda kf is the arrival rate of class K flows with size f. Okay, whose number of packets they carry is f. Okay, so what is a necessary condition for stability? The necessary condition for stability is that when a flow arrives, you decide how many channel uses it gets on channel I. Okay, and then zk is the fraction. So let me just go through this condition. So lambda kf is the arrival rate of flows of type k which have a file size of f. Z is the fraction of flows of that particular class and particular file size that you allocate a particular channel allocation vector h. Okay, so you have flows of a particular class, and some flows of this class you might allocate 2 channel uses on channel 1 and 1 channel use on channel 2, and some flows you might allocate 5 channel uses on channel 2 and then 0 on channel 1 and so on. So Z is the fraction of flows that get a particular channel allocation. Okay, and of course that's the workload on channel I, and this total summation of course has to be less than 1, right? So that's the workload on channel I. Workload is basically the number of time slots that a particular channel is used. Okay, that has to be less than 1. Okay, so workload simply means the number of time slots a particular channel is used, and of course there are other conditions. Clearly the summation over all possible channel allocations should be equal to 1. This is the fraction of time, so this fraction should add up to 1. And you have this condition. Suppose you have allocated channel I to user a particular flow. Okay, and I'm going to here again make the argument that later that we'll transmit a user on a channel only when its state is the best possible on that channel. So therefore the total rate allocated to a particular user must be greater than or equal to file size. Okay, otherwise the user cannot be served. Okay, so these are the necessary conditions for stability. Is this clear? So the basic idea is that you're looking in terms of the number of time slots that you allocate to a user, but somehow we have to figure out when a user arrives, how do you determine? So the question is, how do you determine these quantities? Okay, so when a user arrives, you decide that I'm going to give it so many time slots on this channel, so many time slots on some other channel, so many time slots on some other channel, and so on. If there is a way, if the lambdas are known ahead of time, then of course you can compute these quantities. Okay. The question is, in general, the lambdas are not known ahead of time, so how are you going to compute these quantities? So when a user arrives, is there a way to select the number of time slots the user should use on a particular channel without knowing the arrival rate? Okay, that's the question. So the necessary conditions can be translated to throughput optimal algorithms using this connection between optimization and stochastic networks, which have been explored for wireless networks over the last several years. These are some of the first papers on this topic. Let's just look at a simple feasibility problem. So this is just a constant, just pretending that this is an optimization problem. I'm really looking for a feasible solution to figure out what is the fraction of time I'm going to use a particular channel allocation vector. Okay, so these are just the constraints that I wrote down in the previous page. Okay, and what I'm going to do is I'm going to take this constraint and append it to the objective using a Lagrange multiplier Qi. Okay, and so if you look at this optimization problem, okay, if the Lagrange multipliers are given, it is just minimize Qi times this quantity. Okay, and this minimization can be carried out for each k and f. And in fact, it can be further decomposed into doing it for each file. And so the minimization problem actually turns out to be a simple problem. I mean, well, I don't know how simple it is, but it does. So it allows you to calculate the channel allocation vector ahead of time. Okay. So let's say, so if Qi, the Lagrange multiplier corresponding to channel I, let's say, is given to you. Okay. Then what you do is the number of time slots hi that you allocate to a particular to this flow when it arrives is just simply to minimize summation Qi hi subject to this condition that you give sufficient service to that flow. Okay, So this is very similar to the max weight algorithm, except that it's a minimization algorithm. So you're trying to minimize workload across the various channels. Okay? So it turns out that the max weight algorithm can also be derived purely from optimization considerations, and this is a sort of a minimum load. So this is a min weight load balancing algorithm that also can be derived from optimization conditions if you can identify what this QI is. Okay? So this is, so the Lagrange multiplier is given. So what I'm going to do is that if I have 3 channels, okay, I know the Lagrange multiplier corresponding to each channel. I'm going to decide how much of my effort how much this user is going to be served by channel 1, channel 2, and channel 3 by minimizing this quantity. But of course, under the constraint that the amount of service that I give to this user is greater than or equal to its file size. Okay? So now how do you compute these QIs? These Lagrange multipliers are still unknown to us. So if you look at the QIs, the Lagrange multiplier is just nothing but the Lagrange multiplier corresponding to this constraint. And this constraint is just the left-hand side tells you the rate at which workload is arriving to channel I, and the right-hand side, hopefully, if you schedule correctly, would be the rate at which you're draining the workload. So the workload on channel I seems to be a good guess for an estimate of the Lagrange multiplier. Okay? Of course, the workload is a stochastic quantity, so it's not exactly ever going to be the Lagrange multiplier, so it's going to go up and down and so on. So it's not the Lagrange multiplier, but it is a good guess for an estimate of the Lagrange multiplier. So it turns out that this is the right guess for the Lagrange multiplier. Okay? So the scheduling algorithm then is as follows. So you're trying to minimize this quantity. So what you do is that at each time instant when a flow arrives, okay, you allocate the number of time slots you're going to allocate to the flow based on the workload. So you look at the workload on each channel. So what is the workload which you have already, so there are already flows in the network, right? So there are already flows in the network, and flow 1, for example, has decided I'm going to use 3 time slots on channel. I'm going to be allocated 3 time slots on channel 1 and 6 time slots on channel 2. Okay? Some of these allocations have already been taken place. So you look at the remaining number of time slots you're going to allocate to a particular flow on a particular channel. Okay? And you add them all up, and that is QI. So QI is the workload, that's the remaining workload on channel I, added up over all the flows in the network. Okay? And when a new user arrives, you look at this workload and you minimize this quantity subject to the fact that the allocated number of time slots on all the channels is larger than or equal to the file size of that flow. Okay? So is this algorithm clear? Or okay. So it's basic. Yeah.
The constraint always feasible because you can always choose make longer HI longer, right?
Right. Exactly.
Yeah,
Exactly. So HI is the number of slots you allocate to the particular user on channel I. So you keep increasing that till you. Of course, there's a trade-off here. So you're minimizing this quantity, and so it is exactly like the max weight algorithm, except that it is a min weight algorithm. So it's a load balancing algorithm in a sense. Okay. Any other questions? Okay. So and the scheduling algorithm now is as before. Now once it's been allocated, once the channel, once the flow has been allocated, once the number of users of a channel are fixed for a particular user, what you do is that if you have any workload remaining on a particular channel for a particular flow, you try to satisfy it. You wait for the channel to reach its best channel condition for that user and then transmit. Okay, so that's the algorithm. So there are 2 issues here. One is I assume that RF max is known. So I assume that somehow. So what does the base station know? So the infrastructure. So you can probe the channel and you can try to understand what the current channel conditions are, but you cannot know what the best channel condition that a user would see. Okay, so that's an unrealistic assumption. Then even if that is known, how does this algorithm perform? And this is somewhat of a, so we chose an example to illustrate a point. The point here is that if you use the algorithm that we are proposing, it is throughput optimal in the sense that for a larger arrival rate than the max weight algorithm, it continues to be stable. But on the other hand, the max weight algorithm actually performs much better. Okay, the max weight at light loads, the max weight algorithm performs much better. Okay, and the reason is that flows don't arrive instantaneously. In this model, I assume that, so when I gave you the example with 3 flows, I assumed that all 3 packets are available to you for transmission immediately. But let's say you are sitting at your BlackBerry and you're downloading something, which you're not supposed to be doing because it interferes with the talk. Suppose you're doing that, then actually let's say you're looking at CNN's website. Okay, then CNN's website, all the packets don't arrive to the base station or arrive to your whichever your scheduling authority instantaneously. Actually, packets arrive one at a time. Okay, if these flows are sufficiently long, okay, then one could argue that roughly in the time scale of interest, the max weight algorithm is actually a good algorithm, right? So on the other hand, if you look at the data that Qualcomm and Motorola have, most of the packets are actually very small, and so you have to somehow, it seems like at light loads, the max weight algorithm is good, whereas at heavy loads, this workload based algorithm is good. And the question is there a way to amalgamate these two and actually get a curve that sort of is as good as the max weight algorithm at light loads and becomes better. Of course, I mean this is an exaggerated example. Of course, this example, I mean, you know, this difference depends on the traffic mix that you have. If you look at the traffic mixes that depending on the time scales of interest, I mean, over very long periods, you could have very short files, in which case this algorithm will always be better. But I just wanted to illustrate a point here by showing where it could go wrong. Okay. So there are sort of 2 issues here. One is not knowing the Rmax, and the other one is performance. So Rmax is not knowing Rmax is not a major issue. So what you do is that just for each flow, just remember the best channel state that you have seen so far. Okay. Ultimately, you're going to see the best channel state that a user has seen. From a purely stability point of view, not knowing Rmax is not a major issue. The only thing is that ties cannot be broken randomly. Okay, so if 2 people are, so if you don't know the best channel condition for each user and you're estimating it, you don't want to break ties at random, ties arbitrarily, actually. The reason is that when a new flow arrives, okay, it would have seen only one channel state, for example. Okay, so all new flows would always look like they're in their best channel state, so you might always be scheduling new users, which may be bad for the system. So a random tie breaking rule or oldest first tie breaking rule seem to be good tie breaking rules. So for these kind of rules, we can prove throughput optimality. Whereas if ties are broken arbitrarily, we don't believe it is throughput optimal. In fact, we've done simulations to indicate it's throughput optimal, although I don't have a proof that it's not throughput optimal in general. But it seems like what the reason seems to be, if you keep always serving the new flows, something could go wrong. You want to I think the basic requirement you want for a good tie breaking rule is that when the number of users become large, then the probability you're transmitting a user which is in its best channel state should go to 1. Okay? And it doesn't seem like that condition would be satisfied if ties are broken arbitrarily. Okay? So this is unlike the max weight algorithm, so you have to be careful when you're doing this learning. So when you're learning the maximum rate at which a user can transmit, there are also practical issues. I mean, suppose what happens if a user sees its best channel condition but sees it very rarely. The probability of seeing its best channel condition is very small. Then you may make that user wait for a long time. So in practice, you may want to use the window over which you're learning and so on. So those are practical details I'm going to ignore. But the bigger question is flows don't arrive instantaneously. So the question is, should we start schedule? So even if a flow doesn't arrive instantaneously, the question is, if a flow doesn't arrive instantaneously, you cannot calculate its workload. So you cannot do this minimum min weight load balancing algorithm that I mentioned. So since you don't know what the size of the file yet is, okay, so the entire file hasn't arrived, you don't know the size of the file, so you cannot implement that algorithm that I mentioned before, because it has a constraint that the number of channel states you allocate should be such that the file can be served. You don't know what the file size is. So what do you do in this case? And maybe you should start scheduling a flow immediately as soon as the first packet arrives. And sometimes maybe you should schedule a flow even when it's not reached its Rmax. And the answer to that, both of them, is yes. There is a way to do this while preserving throughput optimality while improving performance dramatically actually. So we divide flows at the base station into two types of flows. So we call a flow transient if the last packet does not arrive. So the flow is still, other packets in the flow are still are yet to arrive. And the resident flow is one that's already the complete file has been transferred to the base station. Okay. So the max wait algorithm, so if the flow is really persistent for these type of flows which appear to be persistent over a long period of time, max wait algorithm is clearly better. Okay. Whereas flows that are very small and arrive to the base station quickly, then this workload based algorithm is better. Okay. So what do you do? It turns out the best thing to do would be to do a hybrid algorithm. The algorithm is that each flow, when it arrives, records the backlog or the workload in each channel. So QIBF is the workload in channel I when flow F arrives. BF is the begin time of a flow. So when a channel arrives, when a flow arrives, you record the queue length. Okay. So the reason you record the queue length when a flow arrives is that if you know everything about the channel, the Rmax for example, then you can, and if the flow has arrived fully, then this is what you would be using for your max wait algorithm. Whereas if you don't record it at that time, then the queue lengths might change later on, and that may not be the right your estimate of the. So what you're doing may not be the right thing, at least according to what the optimization algorithm suggests. So what you do is that if you see a new channel condition that is better than the best channel condition you have seen so far, then you recompute your channel allocation. So when a flow arrives, you record the workload on each channel, okay, and then as the flow stays in the system, you update the maximum rate at which the flow can be transmitted in each channel, and you keep changing your allocations as your estimate of this changes. Okay. So that's one part of the algorithm, and the other part of the algorithm is that which flows to transmit. So should you transmit a flow that's already in the system, okay, or do you transmit a flow that's still, whose packets are still arriving from the base station? So what you do is that you can use a very simple algorithm like this. Look at the number of packets in the transient flows that are yet to fully arrive, and look at the number of packets that are fully of the flows that are fully arrived. Okay. If the number of transient packets is greater than the number of resident packets, okay, then you use the max wait algorithm. Okay. On the other hand, if it's the other way around, then you use the workload based algorithm that I mentioned amongst the flows that have already arrived into the system. Okay. So for flows, so essentially the idea is that for flows that are still arriving, you use the max wait algorithm. Okay. So assume that they are going to be persistent. So pretend that these flows are going to be persistent, and we know for the persistent flows, the max wait algorithm is good. For flows that have fully arrived into the system, as I mentioned earlier, for throughput optimality, you need to transmit a flow only when it sees its best channel state. Okay, and this algorithm tries to combine the two, and what it says is that look at just the total number of packets in the system, and this can be justified again using this optimization sort of way of thinking about it. and if the transient flows are selected for each channel, you use the max wait algorithm. Just simply amongst the flows that are still injecting packets into the network, just simply do the max wait algorithm. And for the other flows, do the workload based algorithm, and then to decide which one of these flows you are going to transmit, you look at the total number of packets waiting for each flow type. Is this clear? Is the algorithm clear? So we make the assumption that the injection period of a flow is upper bounded. Okay, so this assumption implies that if you have a flow of finite size, okay, so we are going to assume that there is some algorithm or protocol which guarantees a minimum rate for the flow into the network, so that the amount of time that it takes for a flow to get into to arrive at the base station is bounded. Okay, and the number of incoming flows per time slot is upper bounded. Both of these assumptions can be relaxed, and if the tail falls off quickly enough, these assumptions can be relaxed. But the basic idea is just to think about it this way, and then you can relax it easily. It's an epsilon delta argument to relax it. So the hybrid channel assignment and workload-based scheduling algorithm is throughput optimal, which the hybrid again. So you use the max wait algorithm for the transient flows, and the workload-based algorithm for the resident flows. So the point is that the number of transient flows in the network is going to be upper bounded, okay, because the number of flow arrivals in a time slot is bounded, okay, and the injection time is bounded, okay. So when the number of flows is very large, okay, so most of the flows would be flows who have already arrived into the network. The number of flows that are still arriving is going to be bounded, so we don't have to worry about them at all. And essentially, for the other flows, for the flows that have already arrived into the network, when the number of network flows is large, the probability of flow is served before you correctly learn its RF max is going to be small, okay, because the flow has been in the system for a long enough time. If the number of flows is large, that means that some of the flows have been in the system for a very long period of time, and then those flows you have learned the RF max correctly, and you have to deal with the other flows carefully and so on. But that's the basic idea. So the number of transient flows in the network is upper bounded. I mean, and this assumption, of course, if you relax this assumption, these things are not going to be true, and you have to be more careful in doing the proof. Okay. So this algorithm, so this is the same picture that I showed you before. So it's a single base station. You have 5 channels, okay, and the average file transfer delay is something we plotted here. So this is the workload-based algorithm. This is the max wait algorithm, okay. So if you combine the two, and this is not just one example, so almost all the examples we've done extensive simulations, it always seems to do this. I mean, it picks up. It looks like the max wait algorithm up to this point, and then it continues to be stable beyond this point, okay. Whereas the max wait algorithm blows up like that, okay. I think at some point these two will start meeting up, but up to what we have shown here, it seems to correctly adapt itself. We don't have a good explanation for this, but it seems. I mean, all we have been able to prove is stability, okay. But it seems to correctly. I mean, it seems to adapt to the right algorithm at the right time. Okay. And as I mentioned earlier, and I guess it was related to Peter's question, is so when the number of users become very, very large, it's hard to argue that the channel states are independent across users. Okay. But in real networks, the number of flows in a cell is actually limited by. I mean, you assign codes to the users, or you assign various system resources, and so the number of flows in the network is bounded. And in this particular example, actually, the max wait algorithm is much better than our algorithm in terms of. This is one example. Of course, you can have all kinds of other examples. I think this is an example where we chose the file sizes to be skewed in such a manner that there are lot of large files. So in this algorithm, actually the max wait algorithm has a much better blocking probability than the workload-based algorithm, but the hybrid algorithm beats both significantly. So it seems to work better than the max wait algorithm and the workload-based algorithm. Okay. So I want to leave with some conclusions and open problems. So when you have flow level dynamics in the system, and the number of files in the system can fluctuate because the number of packets in a file is finite, max wait is not enough to ensure maximum throughput in the network. So that's the example that Van de Ven, Bost, and Schneer came up with. And so what we have done is shown that in general you need actually a min weight load balancing algorithm. Somehow you have to figure out a load balancing algorithm, but it seems to work very similar to max wait, except that it's sort of in some sense a complement of it. You look at the workload on each channel, okay, and try to minimize the weighted sum of the workload times your resource assignment. But interestingly, even here max wait helps with performance at light loads and when the number of files is very, very large. Okay. So the hybrid algorithm automatically seems to pick up the good qualities of both algorithms and works over all kinds of traffic mixtures. If you have a large a mix of very small files and a few large files, or the other way around. So in some cases the max wait is clearly better. In some cases the workload based algorithm is better. But the hybrid algorithm seems to stabilize the system and lead to good performance. But one thing that is unclear is that, so the characterization of performance. There's a lot of work showing heavy traffic results for the max weight algorithm and the related algorithm called the back pressure algorithm for in the case of fixed number of flows. So in this context, it's not clear how to guarantee good performance. So as I mentioned here, when you're learning the maximum rate at which a user can transmit, it's not clear that you could break ties arbitrarily. So you have to have good tie-breaking rules. And how do you characterize the performance of good tie-breaking rules? I mean, depending on the choice of the tie-breaking rule, there's some variation in performance. And the question is, how do you select good tie-breaking rules? And we don't understand this question at all. I mean, average. So all this entire talk has been focused on average queue length. So what if blocking probability is the right metric for your system? And finally, the question that Peter asked: what if the channel states are correlated across users? We fundamentally rely on the fact that the channel states are independent. Okay, which seems like a reasonable assumption. If it's a large area that the base station is serving and the number of users is like 50, that the average separation is sufficiently large that the fading states would be uncorrelated. But on the other hand, it's an interesting curiosity. What happens when the number of users gets large, which you're allowed in this model, in which case channel states will not be correlated, and then what do you do in that scenario? Okay, thank you.
Are there any questions?
I had a question about how you'd learn the channel state. You assume that once you've learned it stays at this max rate, or is it allowed to?
We keep changing it time instant to time instant. So you look at the best channel state you've seen so far, and you see a channel state better than that, and then you call that your new best channel state. Okay, and ultimately, of course, you would learn the correct channel state. In general, it'll keep changing over time. Hopefully, if you wait sufficiently long, then the probability that you have the wrong channel state is small, and so that's why it works.
Presumably, your hybrid policy, you can also introduce a parameter that allow you to use more aggressive using max weight or more aggressive using the other one, right?
Right.
And in your simulation, you have particular choice.
Right. You could have anything like alpha times the one type of packets greater than or equal to something would work. So that's something that we don't know what the right. I mean, it seems to depend a little bit on the traffic mix, but uniformly, if you just use for various simulations that we tried, it seems to just looking at the total number of packets seems to work, but that's not the complete answer. So we don't know anything about performance. That clearly. So we know that works if you make it alpha times something. So instead of weighting them equally, if you weight them in some other manner, then it's still stable. But the performance, of course. But I think that might depend on what kind of traffic mix you're looking at. I guess from what I've heard, mostly it is small files, and occasionally there are these large files. So it's unclear how to make use of that too. Maybe that should be somehow. Maybe the traffic statistics matter in terms of how you choose the weights.
Well, let's thank the speaker again.